So today we're going to talk about how we can sum or find the center of mass for things that are not discrete, right? Originally we started with our formula where we had mass times distance away from some arbitrary starting point we decide to pick for each mass, all n particle masses on the system. And we divide that whole thing by m. But sometimes this is really hard to do, right? If we had infinite little things to sum up, then we can't exactly use the sigma, right? Let's go with the example of a rod. Let's say we had a thin, one-dimensional rod. I know, not possible, but let's imagine it's so thin it's almost one-dimensional. We can estimate it as one-dimensional. Let's say that somehow the mass starts at like 0 and it increases until it gets to some mass m, or some mass small m, right? M final. So you notice that we have a different mass as we go along the system. How many different masses do we have? We have infinite different masses because it changes the whole time we're going along the distance of the rod. Well, if I know one thing about integrals, right, it lets me sum up these little changes over little distances until we get the whole sum. So I am actually going to say, let's say this rod is of length L, starting from the leftmost point, right? Then all I have to do is I have to integrate along the whole length, so I'm integrating from 0 to L along the whole length of the rod. And I'm integrating, right, I need my R, right, times a change in mass, right? I'm going to have a different mass, so for every distance R, right, let's say R is like here, I'm going to have a tiny piece. I can take a tiny piece and find what mass that is, right? R times dm, which is like my R times m here. And then I just have to divide everything by m. Alright, so that seems simple enough. But now the question is, how do I find a relation between R and dm? Alright, so we can find that relation, or we don't have to find that relation. On the AP test, if you get a problem that's asking you to find like the center of mass on like a continuous rod or something, they'll give you something called linear density. So you know normal density is mass over volume, m over v. But linear density is something different. It's our change in mass, right? Still mass on the top. But instead of volume, we just have a length. Right? Volume is three-dimensional, length is one-dimensional. Like it's on a line. We're integrating along a line, so that's why it's called linear density. So they'll give us some linear density. Let's say that they give us that the linear density is proportional to R, right? So in my rod, right, what would this look like? In my rod, if I am 0 distance away, right, if I'm 0 distance away, my mass would be 0, right? So here is length, and then here's mass. Right? My mass would be 0. At some R here, distance R here, my mass would be R. And yeah, so that's pretty much just what this means. Okay. So how do we use this to our advantage in plugging it into this equation? Well, what you do is you know that lambda, right? Lambda, or our linear density, is equal to dm over dr. So I can multiply, I can just get rid of this part for now, and then I can multiply both sides by dr, right? So I get r dr is equal to dm, right? R dr is dm. So here, instead of having dm, what I can do is I can say, okay, I replace dm with r times dr. I can integrate this, right? This is just the integral from 0 to L of r squared dr, and we divide by m, the whole thing by m, which is the total mass of the system. Okay, so what now? Okay, so all we have to do now is we integrate the top, and we get integral of r squared, right? That's r cubed over 3. And then we integrate, our bounds of integration are from 0 to L, so r cubed over 3 from 0 to L, right? So we just plug in L pretty much, but we got to keep our M. So what do we get? We get L cubed over 3, whole thing divided by M. So that's, we're one step closer. But now we need to find the total mass. Okay? So to find the total mass, all we have to do is we realize, all right, we still use our linear density. We realize, right, our linear density was R. Okay, so we can say that if I have this rod, right, to find the mass, I just have to integrate about the whole rod, right, 0 to L, right, the change in mass. Right? it's just like if I wanted to find what like x was, I would just integrate dx and I get x, right? If I want to find what the total mass is, I integrate dm, the change in mass, along the entire system to find the whole mass. Again, right? I plug in my relation that dm equals r dr, right? So if I integrate this, I get integral from 0 to L of r dr, and what do I get? I get r squared over 2 from 0 to L, and this ends up being just ends up being L squared over 2. Okay, so now we plug in L squared over 2 here, right? And what do we get? I'll write it over here. We got L cubed over 3 on the top, L squared over 2 here, and we end up with 2/3 L. The center of mass is going to be 2/3 the way from the left side. So we say our center of mass is right here, 2/3 of the way from the left side. Yeah, so that's basically an example of how you would use this kind of thing in order to find our linear density, or our center of mass, given a linear density. Let's go with one more generic example. So we always want to put everything in terms of length, right? That's why we're substituting dm for something dr. Because we know our length, so we know our bounds of integration with respect to distances, but we don't exactly know everything with respect to masses, right? We only know the change in mass over distance. So that's why we want to put everything with respect to distance. So now let's say that my lambda is equal to some f of r. Alright? Okay, if it's some f of r, I can write my dm is equal to, or dm over dr is equal to f of r, right? So I can say dm equals fr, right, dr. So if I wanted to find the center of mass, right, my integral for some length along a rod is just going to be r dm, right, r dm over m. Remember, we want to write everything in terms of lengths, so this is going to be integral from 0 to L of dm, right? But then we can substitute this for dm, so we get integral from 0 to L of fr times r times dr over integral from 0 to L, L of fr dr. And this is a more generic way to find the center mass of some non-uniform rod. You notice, right, we just take our linear density, we did some rearrangements, we plugged things in, and we got this final formula. So if you're ever confused, right, just keep this one in mind, right? Maybe take a note of it, keep this in mind, right? It's pretty simple to remember. You integrate along the whole length. On the top, you want to find r dr, right? So you do f of r times r. That's why, right, r dm. But on the bottom, we just do dm. So we have the same thing, except we don't have the r. And there you go. That's the basic way to find, center mass of a non-uniform rod. There you go. You better do well on the AP test. Let's go.